in conclusion, with all the of all the new material that you'll be responsible for, at least for this class, we'll do modular arithmetic. Okay, now there's a little bit of work we have to do to make sense of it all, but again, this is something that's extremely important in computer science. You use it whenever you tell time, okay, without thinking about it. It also is an important source of fields. So remember we had the field axioms, okay, and we'll talk about how we can get some fields out of this construction. The ones that aren't fields are rings, which you haven't really heard. Yeah, you've heard me say the word before, but you haven't seen those, but you'll see those very quickly in your first abstract algebra course. Okay, so let's go ahead and make the definition. So we will define an equivalence relation on Z, and so this is what the equivalence relation is called. I know it looks complicated, okay, for any k an element of Z. Okay, so we're taking the integers, that's our underlying set, and then we pick up some k, and we're going to define this equivalence relation that depends on k. Okay, so if we pick up m and n an element of Z, right, we want to decide when are they equivalent to each other. So m is equivalent to n mod k, provided k divides m minus n. And so you say, well, I thought we were going to calculate. Okay, well, we'll get around to that. We'll do some fun calculations in a little bit. Okay. So first of all, just in the abstract setting, let's go ahead and check that this really is an equivalence relation. Okay, well, is it reflexive? And remember, k is fixed here, right? But we're proving this basically for all k, because nothing that we do will depend on the particularities of k except that it's an integer. Okay, so how do I show that m is equivalent to itself? What do I have to write out? Here's my definition, right? So instead of m and n, I'm just doing m and m. So does k divide this quantity when m equals n? Because what is that? 0. And everything divides 0, right? Okay. So for every m an element of Z, m is equivalent to m mod k, since m minus m equals 0, which is divisible by k. Doesn't matter what k is, right? It says mod k in there, okay? Right? All right, what about symmetric? Okay, so what's my opening line for symmetric? And I'll give you the opening word, suppose. Because symmetric is an if-then statement, right? So what do we suppose in this case?
Suppose m is equivalent to n mod k?
Yeah. So suppose m is equivalent to n mod k, and then we just write out what that means. right? That means that m minus n equals ka. So I'm writing out here now what it means to be divisible by k, right? For some, yes, for some a, an element of z. So what am I trying to conclude here? What's the equation that I need now?
N minus?
Yeah, I need to consider n minus m, right? But n minus m equals what? How should I write this now?
Equals negative AK?
Yeah, or k times minus a, whichever way you want to do it, right? So k divides n minus m, which is equivalent to n equivalent to m mod k. Now we could have done this a little bit more quickly using a theorem, right? We know from previous stuff that if k divides some number, then also k divides minus that number. It's a simple linear combination, right? But okay. So I'm not being lazy, right? But anyway, I thought I would give that detail there. Okay? And also I wrote this detail out because it's going to help us a little bit with the transitive. So what do I suppose now? And let's jump right to the heart of it, okay? Let's just use the definition of what it means. Okay, so I'm going to suppose that m minus n equals ka and what? Since I'm doing transitive, give me some letters. So here I'm assuming that m is equivalent to n mod k. For transitive, what do I need next?
N minus L?
Okay, sure. We'll use L. And of course you need n because remember we need m, we need n, and then n has to be equivalent to something new. So we're using L. You know, k is kind of out of the picture here, right? Okay. Minus L equals what?
KB?
Yeah, we need a new integer here too, right? And then, of course, I need to write what? For some what?
For A and B elements B.
Yep. Okay? So everybody see what I did here? I just because I don't want to take too much time with this, but I just went directly, instead of writing this out, m equivalent to n and n equivalent to L, we're just writing down what it means. M minus n equals Ka and n minus L equals Kb for some A and B, an element of Z. And what should my closing line be?
M minus L is equal to K.
Yeah, M minus L equals K times something, right? Where something is an element of Z. Right? That's where I'm headed. Okay? Everybody with me? Well, let's sort through it and see. Maybe you've already done the calculation. Okay. So, everybody agree this is where I need to go. I need to have that m minus L is divisible by k, which means that m minus L is equal to k times some integer. And I don't know what it is yet, but I have to find it in here. Okay? So, I have m minus L. Okay. I need to use the information that I have up here. And the information up here involves a letter that has disappeared in this. It involves n, and n is gone. Okay? But you know the thing. Sometimes, well, I sure would like to have that n back. Okay? So I can use that information, so what do?
Put it back in there.
Put it back in there, okay. So equals, and how am I going to put it back in there?
M
I got to put it in, I got to take it away, right? Okay, and I'm after m minus n, so why don't I subtract the n and then add the n back in, right? And lo and behold, I have n, and then I have minus L, right? Okay? And now what? Now I just collect stuff, right? So this equals, so m minus n is Ka, so we heard the right answer already, right? Okay. Plus Kb equals K times A plus B, where A plus B is an element of Z. So that tells us that M is equivalent to N mod K. Not N, L, which is where we wanted to finish. Okay? Lovely proof to put on the test. I say that as an inducement to, again, go through and work through the proofs of things that we do in class. It should be the first thing you do before you start on the homework. All right, any questions about this? This is, in fact, an equivalence relation, okay? And it's a very useful and important one. Finds its way deep into the heart of physics, for example, okay? And even in chemistry, right? Things like spin. Okay, so. And of course, computer science. All right, let's try some examples. It's funny, I don't know why I left it out, but I didn't consider k equals 0 in the text, but hey, let's do it, right? Okay. So what does that mean? So again, for each k, we're going to get a different equivalence relation, and we're also going to get different equivalence classes, okay? So let's see what this means. So m minus n equivalent to n mod k. What does that mean? That means that m minus n is divisible by 0, right? And how many things are divisible by 0? Namely, 0, okay? So what does that mean? So that means m minus n has to be equal to 0, which means what? M is equal to n. So this is one of our trivial equivalence relations, right? So m equivalent to n mod 0, 0 in there, means precisely that m equals n. So the equivalence class of m is just what? You know what you're saying, but you know not what you say. The set containing m. Okay, right. I mean, you know what you're talking about, but let's be real precise about this, because the equivalence, remember, the equivalence class is a set. It's the set of all things that are equivalent to m. And what we did up here tells us that the only thing that's equivalent to m is itself. So this is one of our, remember last time we did these two sort of trivial ones, right? So this is the trivial one that puts every element into its own little set, okay? So it chops up the integers basically into, well, the integers, right? You're just putting brackets around everything. So this one's completely uninteresting. So this is trivial. Okay, so we don't really talk about Z. Let's see, did I give you the definition? No, I didn't. Okay, we'll do that in a second. Okay. Let's look at next most interesting, but also trivial example. Okay, so m equivalent to n mod 1, what does that mean? That means that m minus n is divisible by 1. And how many things are divisible by 1? everything, okay? M minus n is basically an integer, because every integer is divisible by 1. Well, how often is the difference between two integers an integer? Like always, okay? So that means that m equivalent to n mod 1 is always true. Okay, so now what is m bar? If I pick up any m, what is m bar? Z. So this is the other trivial one where the entire set is one single equivalence class. Okay? Because everything is equivalent to everything else, it all gets lumped together. This is also one of our two trivial ones. Okay.